Okay, students. So the noise is there. So let us go for the introduction of noise. So noise is defined as an undesirable electrical energy, that falls within the passband of the message signal. This gives rise to an audible noise in a system. The presence of noise degrade the performance of the communication. So always the presence of noise degrade the degradation of the performance of the communication system. So in this chapter, we have to analyze the noise in continuous wave modulation system. For such analysis, we first define the receiver model. Then you have to analyze the noise in AM receiver, namely DSBSC, SSB. Finally, you have to discuss the noise in FM receivers. So in a system, the noise has to be introduced. So the noise is degradation of the system performance. So what is the system in the communication? That should be the transmitter, channel, and the receiver, all together called as a system. So the system performance means the ability to receive the signal at the receiver end, but you have to transmit the signal at the transmitting end. The ability to receive the signal at the receiving end, what you are transmitted the signal at the transmitting end. Okay, 100% signal has to be received at the receiving end. So that is the perfect system. Now, if the system performance is, if the signal not 100%, if suppose the 50% is degraded, that is the damage, that is quality is deteriorated. Now, that is the how much percentage of signal is affected by the noise. Okay, all those things has to be going to be analyzed now. So first of all, we have to some receiver models are there. So in the receiver models, AM receivers and FM receivers are there. Already discussed the AM receivers and FM receivers. AM receivers basically the modulation which are used in the receiver and the demodulation in the receiver. So the system seems to be DSBSC and SSB signals. That is double sideband suppressed carrier system and single sideband system. And finally, we have the FM receivers. So because of we have to analyze the noise in the system. Okay, so it is the receiver model. So in the below figure, you have to show that the receiver model. It is the receiver model. It says the modulated signal given to a summer, modulated signal S of t, modulated signal S of t, and noise is there, W of t. S of t and W of t is added because of it is the summation sigma. S of t is given and W of t is given. W of t is the noise. S of t plus W of t is given to a band pass filter. Now the band pass filter output is given to demodulator. The demodulator output is output signal. This is the receiver model. So in the receiver model, the characteristics are like this. So this is a characteristics curve. It has to be n/2 the noise for spectral density, and BT is the bandwidth. So there is 0 to positive axis and 0 to negative axis. So this is the receiver model. For the receiver model, the modulated signal given to a summer and the noise is added there. After adding and these two signals, that is modulated signal and noise, the signal output is given to band pass filter. Band pass filter output is given to a demodulator. The demodulator output is output signal. That is X of t is the received signal. X of t is equal to S of t plus W of t. S of t plus W of t. So now in this model, the figure shows that receiver model is the most basic form. The modulated signal is S of t and noise is W of t. Signal W of t known as front end receiver noise. The receiver input signal is the sum of S of t and W of t. The output of band pass filter is X of t. The bandwidth of the band pass filter is kept just wide enough to pass the modulated signal S of t without distortion. So the bandwidth is wider. Bandwidth is wider. That is the model. The model is like this now. So the demodulated process represented by the block that is demodulated depends upon the modulation use. Or the modulation use. So modulation use in AM, the demodulation AM. The modulation is FM, the demodulation is FM. So now for receiver model, we may denote and define the following things. The receiver model, we may denote and define the following things. What are the things that are the following? These are the things. That is, we denote N out of 2 as a prospective density of the noise, the WOT, for both positive and negative frequencies. That is, a noise has the prospective density that should be N out of 2, N naught by 2, that is zeta by 2. Prospective density. Where N naught is the average noise power per unit bandwidth. N naught is the average noise power per unit bandwidth. And bandwidth of band pass filter is equal to transmission bandwidth of the modulated signal, and it's denoted as B of t. That is bandwidth of the signal. And midband frequency is equal to the carrier frequency, and it is denoted as FC. That is midband frequency is carrier frequency. So that is denoted as like this now. So this is the signal. This is the figure idealized characters of the band pass filter noise now. N naught of t is the prospective density of the noise. It has appeared FC, and there is a BT is the bandwidth of the signal, and it should be N naught of t is the N naught of 2 is the an average value. Okay. Now, typically the carrier frequency FC are for greater than equal BT, and thereby and therefore we may consider the filter noise N naught of t as narrow band noise, and it is defined in canonical form as for noise canonical form as N naught of t is equal to N1 of t cos 2 pi FC of t minus N2 of t sin 2 pi FC of t. This is the canonical form. So the filtered signal available for demodulation is defined as X of t is equal to S of t plus N of t. This is the output signal. X of t is equal to S of t plus N of t. S of t is the modulated signal, that is the received signal. N of t is the noise. That is X of t is equal to N of t X of t is equal to S of t plus N naught of t. So the average noise power is given as average noise power is equal to average noise power per unit bandwidth into bandwidth. Average noise power per unit bandwidth into bandwidth, that is N naught into Bt. N naught into Bt. Whereas X of t is the received signal. X of t is the received signal, that is equal to incoming signal S of t, that is modulated signal, plus N of t, N of t, that is the noise. The received signal plus a noise is nothing but X of t. X of t is the received signal. S of t is the transmitted signal, that is a signal, a modulated signal, plus N of t the noise. So now the input signal to noise ratio is given by, that is quality of the signal. The input signal to noise ratio is given by, that is SNR, signal to noise ratio 1. That is average power of the modulated signal S of t by average power of filtered noise and R. This is input signal to noise ratio. And output signal to noise ratio is SNR 0. That is output. Average power of the demodulated message signal. This is modulated message signal, that is input signal to noise ratio. This is average power of the demodulated message signal, is output power, output signal to noise ratio. Average power of the demodulated message signal by average power of the noise. And the channel signal to noise ratio is given by, that is channel signal to noise ratio. SNRC is average power of the modulated signal by average power of the noise in message bandwidth. So now therefore the noise figure is equal to the figure of merit is equal to output by channel noise. That is SNR, signal to noise ratio, output by signal to noise ratio of the channel. This is nothing but the figure of merit. Figure of merit is called signal to noise ratio output by signal to noise ratio of the channel. So now, higher the value of the figure of merit, better the performance of the receiver. The receiver performance is depending upon the figure of merit. If the figure of merit is maximum, the performance of the receiver also maximum. So the value of figure of merit also depends upon the type of modulation used. So that is, so performance of the receiver depends upon the figure of merit, and figure of merit also depends upon the modulation used. Okay. Now, so now go for the one system, that is noise in DSBSC receiver. Noise in DSBSC receiver. So the below figure shows the model of DSBSC receiver. Use a coherent detector. Coherent detector means the receiver and transmitter has in phase and the same frequency. The phase is in phase and frequency is the same. So the coherence means a modulation used a carrier, demodulation used also carrier. The modulation done at the transmitting end, the demodulation done at the receiving. So at the modulation use the carrier, at the demodulation use the carrier. These two carriers are the same phase and same frequency. That is the coherence. Okay, which carrier uses the modulation and which carrier in the demodulation, both are the same. That is known as the coherence. If there is any difference, that is non-coherence. So, okay, in this you can use the coherent detection. Just as the figure, the filtered signal is applied to the coherent detection X of t. It is multiplied with a locally generated sinusoidal wave, that is cos 2 pi fc of t, using product modulator. The product is then filtered by using low pass filter. This is the block diagram of DSBSC receiver. DSBSC receiver is software is going to be receiver applied to the adder. The noise W of T is applied to the adder. S of T plus W of T given to the band pass filter. Band pass filter output is given to coherent detector. In the coherent detector, product multiplier is there, product modulator is there. Product modulator is there. What is the product modulator? That generate DSBS signal. Okay, X of T is there. X of T is nothing but S of T plus W of T. So X of T is applied to the product modulator. The product modulator output is V of T. V of T output is given to low pass filter. That the product multiplier, another signal is local offset signal. That is cos 2 pi of C of T. So where the demodulation X of T is the cos 2 pi of C of T. The local offset also is the 2 pi of C of T. These two signals are the same. That is coherence. Now local offset produces the 2 pi of C of T that is given to product modulator. The product modulator output is V of T. The V of T output is given low pass. The low pass output is V of T. Now this is the model of DSBSC receiver. So now the time domain expression of the DSBSC is given as S of T is equal to this S of T is equal to M of T into C of T. That is M of T is modulating signal. The C of T is carrier. M of T is modulating signal. C of T is the carrier. Now S of T is equal to M of T into C of T is equal to AC cos omega C. AC cos 2 pi of C of T or omega C of T. Now S of T is M of T. AC cos 2 pi of C of T. That is the modulated signal at S of T. Now the channel signal to noise ratio is given as average power of the modulated signal S of T by average power of the noise in message bandwidth. That is SNRC is equal to S of T square bar by NW of T square bar. That is average power of the modulated signal. S of T is equal to S of T whole square is equal to average of the modulated signal is equal to M of T AC cos omega C T of T square whole bar. That is M of T square bar AC cos omega C T whole square bar. That is AC square P into 1 by root 2 whole square. That is power of the signal. That is AC square P by 2. So that is where P is the representation average power of the M of T. That is AC square P by 2. AC square P by 2. That is AC square by 2 now. That is average power of the modulated signal. That is numerator. The signal to noise ratio of the channel is numerator is average power of the modulated signal. That is AC square by 2. The average power of the noise in the message bandwidth is given as n of T whole square bar by that is the average power of the noise for unit bandwidth is equal to n naught by 2 into 2W. That is bandwidth is two times. W is the positive and W is the negative. W plus W 2W. Now 2 to cancel now n naught W. That is the noise power. Now S naught here it's a signal power by noise power is equal to AC square by 2 P by n naught of T. This is the signal. So now output signal to the noise is given as average power of the demodulated message signal by average power of the noise. So average power of the message signal by average power of the noise. That is given as X of T is equal to S of T plus N of T. X of T is equal to M of T AC cos 2 pi of C of T plus N2 of T cos 2 pi of C of T minus this is the noise now N naught of T sin 2 pi of C of T. So this X of T is passed through product modulator. Another input to the product modulator is log loss statistic, that is cos 2 pi FC of t. The output of product modulator is V of t is equal to x of t cos 2 pi FC of t. Now V of t is equal to m of t AC cos square 2 pi FC of t plus Ni of t cos square 2 pi FC of t minus m naught of t cos 2 pi FC of t sin 2 pi FC of t, where V of t is equal to m of t AC. The cos square can be written in the trigonometric identity is 1 plus cos 4 pi FC of t by 2 plus Ni of t, that is equal to cos square, again we have to identify as trigonometric identity 1 plus cos 4 pi FC of t by 2 minus n naught of t by 2 sin 4 pi FC of t. So after simplification of these three terms, V of t is equal to m of t AC by 2 plus Ni of t by 2 plus m of t AC by 2 plus Ni of t by 2 cos 4 pi FC of t minus naught of t by 2 sin 4 pi FC of t. This V of t is passed through a low pass filter now. The output of low pass filter is V of t is equal to m of t AC by 2 plus Ni of t by 2 m of t plus, so the md of t means demodulated d of t plus nd of t, the demodulated noise also, where md of t is equal to m of t AC by 2 is the desired signal component. md of t is the desired signal component, where nd of t is equal to ni of t by 2 is the desired noise component. The average power of md of t is equal to md of t whole square bar is equal to md of t AC by 2 whole square, that is AC square by 4 m of t whole square, that is AC square by 4 into p. Now the average power of nd of t is equal to nd of t whole square, that is ni of t by 2 whole square 1 by 4 ni of t whole square, that is 1 by 4 into area and power spectral density of tau, that is 1 by 4 into n naught into 2w, that is n naught w by 2, that is SNR output is equal to MD is the desired signal of the message whole square bar by the noise desired signal is equal to S square P by 4 by n naught w by 2, that is S square P by 2 n naught w. Now the figure of merit gamma is given as gamma is equal to figure of merit is equal to SNR signal to noise ratio output by signal to noise ratio channel, that is S square P by 2 n naught w by S square P by 2 n naught w. So that is equal to 1. The figure of merit of this system is A1. Thus the figure of merit of DSBSC system should be the 1. Please remember that. The figure of merit of the system should be the unity. So this is DSBSC system. So what you are discussing here, this is the model, the receiver model of DSBSC system. DSBSC signal is given to adder with a noise, that output is band pass filter, then given to the product multiplier. The product multiplier is given to low pass filter. For the product multiplier, another signal is Laplace signal cos 2 pi FC of t. That output of low pass filter is V of t. This is the desired signal. So this is the DSBSC receiver model. The noise added in this system is here the not of t. Okay. So with this, we start the concept of the receiver noise in the DSBSC system. The figure of merit should be the ratio of signal output to noise ratio by the channel signal output to noise ratio. Output signal to noise ratio by channel output to noise ratio is nothing but the figure of merit. So figure of merit of DSBSC system should be the unity. Okay. So the students, please be go through the mathematical equations and block diagrams. Okay. So in the next class, go for another system, that is SSB system. Then go for FM system. Okay. So thank you, Ananda.